Hello, so this video is going to cover the particle model section of paper 1 on physics, and let's see how fast we can get through it. So first thing in this topic is density. Density is fairly straightforward. It's simply just a measure of how much mass you have in a particular volume, so like how much stuff you've got in your space. And there is an equation for this. So there we see density, kind of looks a bit like a P sometimes, people think, but that's actually a Greek letter rho. Then that's mass and that's volume. We've got to remember that mass is in kilograms and volume is in meter cubed for physics. So if you get questions where it's not in kilograms or it's not in meters, you need to convert those first. Okay, so if we link this to our three states of matter, we've got solid, liquid, and gas. I'm going to be drawing these quite a few times on this revision sheet. So solids, you can see that the particles are arranged in a regular pattern. They're fixed in position, so they can't move, they can only vibrate. Now the reason that they're fixed in this regular rigid position is because they have strong forces between the particles. And they're actually, of the three, they're the lowest energy. Because if you think about, if you had something that was a solid, like, I don't know, chocolate, and you wanted to melt it to get it to a liquid, you'd have to put energy and you'd have to transfer energy to that chocolate. Okay, so liquid, kind of in between, the particles are still touching, but they are now irregular. And that applies to both liquids and gases, which I'll come to in a minute. But yeah, the particles are still touching, and the particles, and they kind of slide past each other, okay? So the forces holding them together are weaker than in a solid, and there's slightly more energy in this state as a liquid. Final one being a gas. So let's try to draw this where none of them are touching. Again, it's regular. But one of the words we need to remember when we're talking about gases is random. So we're talking about random positions, random velocities. So remember that velocity is a vector, so it's got direction and magnitude, so it means that they've got random speeds and they're travelling in random directions. Okay, and this one's got the lowest, I should put weakest forces, and it's the highest energy. Okay, so they're the three states of matter. You will potentially be asked questions about their structure, so regular, irregular, fixed in position, touching, lots of space between them, or in terms of their motion. Okay, so remember this one, solid, they can only vibrate about a fixed position. Liquids are free to move, I might just put there, can move. And they sort of slide past each other, and then gases, they're moving with random velocities. Okay, now usually what we see in terms of density is that a solid has a higher density, and as you move down toward a gas, they become lower in terms of their density. You can see that in these particle diagrams, there's more space between those particles in a gas, so there's going to be less mass within a specific volume. Now, this is mostly true, but water, if you look at water when it freezes, the ice forms on the top layer. So that means that the ice, as a solid, must be less dense than the liquid. So if you get a question about that in your exam, just remember that one. Okay, and there is, I've told everyone I'll do some more videos on required practicals, but there is a required practical on density, and there are two versions of this. One for a regular object, regular shape, something like a cuboid, but there's also another one for an irregular object. So this would be something that it wouldn't be easy to measure the dimensions of, and for that you have to use a eureka, or sometimes called a displacement can. But I'll talk about that in more detail when I do that video. Okay, so let's see how we'll go down here. So let's talk about the changes of state. So I'm just going to list these again. I'm not going to draw the particle diagrams, but you need to know the names of the changes of state. So going from a solid to a liquid, remember that's melting. And if you can try and think of examples for each of these, it's a lot easier to remember. So I always try to remember something like, I don't know, chocolate or ice cream, that would melt. And then a liquid to a gas, that is boiling. So you put your water in your kettle, turn it on, and you see steam coming out of the top, that's it boiling. Right, going the other way, gas to liquid. Think about when you're cooking something on a cold winter's night and you see the condensation on the window. That is condensation. And then liquid to solid, the opposite of melting is freezing. So if your ice cream melts, you're going to pop it back in the freezer. Now there are two others. Well, there's one other you need to know going from solid to gas. So it kind of misses out this liquid phase altogether. And that happens sometimes when the temperature difference between something when it's a solid and a gas just causes it to basically gain so much energy that it misses out this liquid phase altogether. This is called sublimation. You might see things like dry ice, so carbon dioxide that's been frozen. That would sublimate when it was put in room temperature. Now the other one I will write just in case. So when you go from gas to solid and miss out liquid, this is called deposition. Okay? All right, now these are all classed as physical changes. Now you might have heard of chemical changes as well. So chemical changes are when bonds are broken, new bonds are made and new substances are formed. Physical changes you can see, if you take like water for instance, water can go from a solid to a liquid to a gas, and then it can go back to a liquid and back to a solid. So physical changes are ones that can be easily reversed. Just by reversing the conditions that caused the original change in the first place. Okay. All right, so we've talked a lot about sort of forces and energy, and you need energy to cause these changes of state. So you either need to transfer energy to the substance to move that way from low energy to high energy, or you need to transfer energy from the substance to the surroundings to go this way. And this links nicely to the next bit I'm going to talk about, which is the internal energy of a substance. Now, the internal energy of a substance is made up of the total kinetic energy, so I'm going to put EK for kinetic, plus the total potential energy, EP. Now, remember, kinetic is all to do with the motion of the particles. So essentially, the faster your particles are moving, the higher the average speed of those particles, the higher the kinetic energy, the average kinetic energy of that substance. And usually you see that as a higher temperature. This one, potential energy, is all to do with the relative positions of the particles. Now this only changes during a change of state. So you've got a change of states here. You can see that a solid, if you transferred energy to a solid, but it didn't change state, all that would happen is these particles would vibrate with a larger and larger amplitude. Okay? If you transfer energy to a liquid without it changing state, they'll just slide apart a bit faster. And gases, if you transfer energy to a gas, they'll move faster. Okay, so that's all to do with the kinetic energy. But when you go through a change of state, you can see you've gone from a solid, where it was a regular structure, to a liquid where it's irregular. You've changed the relative positions of those particles. And again, if you go from liquid to gas, you've changed the relative positions of those particles. So during a change of state, you're not increasing kinetic energy, that would be fixed. What you're doing is you're overcoming some of these forces that are holding these particles together. So you would actually be increasing your potential energy. Okay, so if I just draw a little diagram, a little temperature time curve, you've probably seen these quite a lot, temperature, degrees C, and then we've got time in seconds. If you started as a solid, if you transferred energy, it would increase the temperature until it reached this point here, where a change of state occurs. And remember, on these temperature time curves, whenever you've got a horizontal section, that indicates a change of state. Once it's all changed state, it will then start to increase in temperature again until it reaches another point where it's going to change state to become a gas. And then once you've got a gas, you're just increasing the velocities of those gas particles. Now, there are some energy calculations and equations that you need to associate with these, okay? So when you're increasing the temperature of something, there's an equation that you'll be given, but this is the energy that's transferred to the substance. This is M for mass, this is C for specific heat capacity, and this here is, remember, this triangle means delta, changing, and this means temperature, so it's change in temperature. So whenever you're dealing with a change in temperature, this is the equation you want to use to calculate how much energy has been transferred. So if I just write these in these sections, E equals mc delta theta, E equals mc delta theta, and E equals mc delta theta. Now obviously these will all have different temperatures because they've got a temperature there and a temperature there, and this one's got a temperature there and a temperature here, and this final one's got a temperature here and, well, it's probably a bit higher than that, but a temperature up there. So you need to apply the appropriate temperature change. The specific heat capacity, if anyone can remember, so right, specific heat capacity, we saw this on the energy video. This is the amount of energy required to increase the temperature, I'm just going to write temp, of 1 kilogram of a substance by 1 degree C. Okay, so each substance will have a different value for that. Some substances will require a lot of energy to change their temperature by 1 degree and others less. Okay, but if you ever got a section on a graph that has a change in temperature, you have to use this equation. Now, and that's associated, remember, with the increase in kinetic energy. Now, the bits in between where there's a change of state, there's another equation. And again, this one will be given on your sheet. So energy is mass times this L, which is specific latent heat. Now that is the amount of energy required, I'm just going to put to change the state of 1 kilogram of the substance. Sorry, run out of space a little bit there. So this is all to do with the change in state. If it's to do with the change in state, it's to do with your potential energy. So this section here, E equals ml, and then this section here as well, E equals ml. Now sometimes in exam questions, what they'll ask you is how much energy does it take to increase the temperature from this point to this point and then completely change the state. So you would have to take this whole section here up and across. So you'd have E equals mc delta theta plus ml. And E here, that would be the total energy. Now if they wanted to make it really hard, they could give you sort of 3 sections and you just have to keep adding them. MC delta theta plus ml plus MC delta theta. But we'll potentially do some examples of that in the future. Okay, so the last bit I want to talk about is gases, because there's some information you need to know on gases. But we know that these are particles in constant, random, that word again, random motion. Okay, now for a gas, you need to know what happens as temperature changes. So as temperature increases in a gas, remember you're going to be transferring kinetic energy. So kinetic energy increases, that means their velocities increase. Now, when gases are travelling faster, what they're going to do is they're going to collide more frequently. And because they're travelling faster, each collision is going to transfer a larger force. Okay, so what we'd say is there would be more frequent collisions. That's with each other and with the container. Larger force transferred. And that means that there would be a larger pressure. Okay, so what that means is that pressure is basically proportional, remember that sign again, proportional to temperature. I've slightly run out of space here, but the last thing you need to know is how it changes as volume changes. So if your volume increases, imagine this gas here, if you aren't transferring any more energy to them, you're not increasing the temperature, they'll be travelling around at some random speeds and they'll be colliding at a certain frequency. But if you made that bigger without increasing or changing the velocities of the particles, they're going to collide less frequently. Okay, so for volume increasing, you get less frequent collisions, and that means that the force applied is going to be less, and that means that the pressure is going to be less. So pressure reduced. Oops. And what you see is an equation like this. Pressure is proportional to 1 over V. Now, there is an equation given in your exam which says this. PV equals a constant. So you can see that pressure is proportional to 1 over V. So if you brought V up, P times V is going to be proportional to 1, a constant. Now, if they give you a pressure value and a volume value initially, you can work out what that constant is. And then if they change one of those things, like let's say they doubled the pressure, if you wanted to keep the same constant and you had twice the pressure, you'd have to halve the volume. what I'll do is I'll do some more questions on that, maybe on a separate video. Okay, cheers.